So I am very pleased to present Paul Beckwith. He is a part-time professor at the University of Ottawa, a postgraduate studying and researching abrupt climate change with a focus on the Arctic. He has an engineering background, engineering physics and laser research in the aerospace industry. He has reached the rank of 40 in Canada as a chess master, and is a member of the Arctic Methane Emergency Group. He is here to talk about climate change, and the extent to which is that it is an existential risk. So please welcome Paul Beckwith.
Thank you. So since it's such a small group here, if I've completely lost you, if you have a very sort of urgent question, just throw something at me or stick up your hand or get my attention and I can hopefully answer it. But I'm sure there'll be lots of questions. I've always been interested in climate change. I've always been concerned about climate change, but it was only about 2.5 years ago, that I decided that there wasn't too much else that was as important as climate change. I saw that I had this sense that the planet was rapidly changing, so I went back to school and started in the master's program, and then fast-tracked to the PhD program. There's just so much information to see, and because I'm from an engineering and from a physics background, I had sufficient math and technical background to understand the meteorology systems and to understand the climate change systems from like a physicist point of view, and try to tie in all the different components of the system. So my thesis topic is abrupt climate change, and when I started 2.5 years ago, I really thought it was a toss-up between sea ice being the threshold that was crossed to destabilize the weather and climate system, or the Amazon rainforest. It had undergone a drought in 2005, 2010, massive drought, at which year it became a carbon source rather than a carbon sink. So, because what will happen in the system is, when one threshold is crossed, and it's quite evident that it's sea ice is that threshold, then there can be easily cascading effects causing other thresholds to subsequently be crossed, like, for example, Greenland ice melt or the Amazon rainforest or so on. So I've done some volunteer work for the Sierra Club. I have a blog. I do a blog for the Sierra Club every couple of weeks. If you just go to their main, if you just Google Sierra Club Canada, you'll see it there. And there's a lot of places that do mirrors of that. And I do a lot of advocacy now. Most climate scientists, they have sort of an obligation to let the public know what's going on because there's so much misinformation out there. So let me go on here. So basically, the climate system of the Earth on human timescales, has all these different components, right? I mean, you have your solar inputs, and the sun doesn't change much. There is an 11-year sunspot cycle. The energy from the sun varies about 0.1%. We can see a signal in the climate signal, but it's very small. There has been periods where there's very few sunspot activity for 3, 4, 5 decades. That happened in a period called the Modern Minimum, and we had a sort of little ice age on the planet. So if there is, if it does some long-term stuff, there can be that effect of 0.1% is enough to be noticeable in the Earth's climate, but it's a very small effect. So we're putting these greenhouse gases up. I mean, without greenhouse gases, the average temperature on the planet would be about minus 19 degrees Celsius. So the greenhouse gases trap the heat. You basically have solar energy from the sun coming in. It's all different wavelengths, but it's peaked in the visible, and it warms up the surface of the Earth, and then the Earth emits heat, and heat is basically infrared radiation centered about 10 micron. So that long-wave radiation comes up, and it's the long-wave radiation that is trapped by the greenhouse gases. So you have of course, the hydrosphere component, the terrestrial component, the human influences, the albedo, sort of the reflectance of the material on the surface of the Earth is very important. You also have other effects, volcanoes and then the ice sheets. And then you have in the hydrological cycle, you get the water vapor coming up from the water bodies, evaporation of the water bodies. So we've had about a 0.8 degree temperature rise in the last 100 years, the average temperature rise on the planet due to the increase in greenhouse gases, and that has increased the evaporation rate. So there's about in the last three decades or so, there's been an increase of about 4% increase in water vapor in the atmosphere. So this is important because when you get the water vapor, when you get evaporation of water from the oceans, the water vapor goes up into the atmosphere, and as a gas, it's a clear gas, you can't see it, and then as it rises, it cools and condenses into the clouds. So when you get condensation from vapor in the air, that energy, there's a release of energy. There's the water vapor carries latent heat, and when it condenses into clouds, that heat is reduced. So that provides like extra energy to the storm systems. So I'll give you but the main thing the main key is that we've got the sea ice up in the Arctic, and it's like a white parasol that reflects energy and keeps the Arctic cooler. But that sea ice is rapidly going, extremely rapidly going, and I'll show how it's going. And it's resulting in the Arctic cooling, parts of the high Arctic warming, at about 4 or 5 times the rate that the overall planet is warming. So because the Arctic is warming that much faster, the equator doesn't change that much, so that decreases the temperature difference between the equator and the Arctic. And that decrease of temperature is very key to weather, because what it does is it slows down, through basic physics, it slows down the jet streams that circle the Earth. You could think of the jet streams as kind of like a wall. North of the wall is cold, the air is from the Arctic and cold. South of the wall is from the equator and coming up, and it's warm. So it's like a wall between warm and hot regions. So that because the jet stream is slowing down because of sea ice destruction, the jet stream goes much wavier. And this is what's happening now. So this is why it's suddenly going to go up to 10 plus today, and it was very cold yesterday. Because yesterday we were above the jet stream, we were north of the jet stream, and the jet stream is shifting. It can shift because it's very wavy. It just needs to move a little bit from side to side, and then we can get these warmer temperatures. So, this is going to be, this is why we're getting the weather extremes, because the jet stream is changing character. So as the sea ice goes faster and faster, the jet stream will get wavier. So these weather extremes, people say, well, the last few years have been like among the most extreme years in terms of extreme weather events, and we'll have forgotten all about it in a few years, because this is going to get much more amplified. And the way it will affect people is mostly through food supply, because it really messes up the crop production. But I'm getting that's kind of an overview. So now I'll show you some of the things that support what I'm saying. So this is the methane going back about 800,000 years. So from ice cores on Greenland, we can get information going back about 100,000 years. From Antarctica, the ice is thicker. The rate of snow, the glaciers form on these continents from precipitation getting compressed over many years. So we can go through and look at the layers, and you can see that there's been a cycle of methane. Methane has cycled between, a narrow range, same with CO2 for a very long period of time, and now we're going off into, massive excursion, a massive positive excursion from both gases. The reason why there's a fluctuation here is that the orbit of the Earth changes around the Sun. There's 3 different cycles. The tilt of the Earth changes. We're about 23.5 degrees now. It gives us seasons, and that varies between about 22 degrees and 24.5 degrees. So when the angle is larger, there's more contrast from summer to winter. When the angle is smaller, there's less. If there was no tilt, we would not have any seasons at all on the planet. So this change in the tilt or the obliquity is about a 40,000 year cycle. The ellipticity of the orbit around the Sun, of the Earth in its orbit around the Sun, varies about varies by about 2%. on a 100,000-year time scale. And then the axis of rotation of the Earth, it doesn't always point at the North Star. It kind of cycles or processes around in about a 20,000-year cycle. These are the Milankovitch cycles. These cycles change the amount of energy that's coming at the Earth in a cyclical manner and cause warm periods and cold periods on these sort of time scales. But what we're doing now is, very, very different from that type of thing. Time scale is very important. Sure, the Earth has always gone through ice ages, cooling and warming, but on these type of time scales and within these type of restrictions, like CO2 is varied from about 280. It's varied from about 200 to 300 parts per million, 200 to 280. With these cycles. So when it's, what happens is when it gets cooler, the oceans absorb more CO2, so the CO2 levels drop. When it gets warmer, the CO2 comes up. And, A causes B, B also causes A. I mean, because, if you look at some time scales, the CO2 is lagging. I mean, if the Earth is warming for other reasons, then the CO2 will be following it. But if the CO2 is changing, then it will cause the Earth to change also in temperature. So,
what time scale do you have there? I mean, I
800.
saw a graph, but
Yes. The time scale is this is 800,000 years ago, and this is the present. Okay, so this is basically the extent of the data record from the Antarctica ice core. So bubbles trapped in the ice could be analyzed and give you an idea of give you the gas concentrations of the atmosphere at the time that the ice was formed, and the isotopes of oxygen, the heavy oxygen to light oxygen, gives you the temperature. So we have a proxy for both temperature and the gases, the atmosphere. And then, that can be correlated to many other proxies depending on the time scale. We also have data from marine core sediments going back millions of years. Okay, so this is the mean surface air temperature. So you take the planet, you get the temperature 1960 to 2009. So you take the 2009 temperature, subtract the 1960 temperature. This is the difference. So you can see the variation of warming on the planet. So up in the high Arctic, we have about up to 4-degree temperature change increase in 2009 versus 1960. As you go down towards the equator, it's smaller, and there's even some negative areas in parts of Antarctica. So this is the zonal mean temperature. So if you take a given latitude and take the average temperature across that latitude, that's the zonal temperature, zonal mean, and then you can see how it varies. This is the equator here. As you go up to the North Pole, the zonal mean is much higher, 2.4 degrees. So the Arctic is warming at a much higher rate. The Arctic is warming at a much higher rate than the rest of the planet. Okay, there were a couple images here. I'm not sure they're not showing up properly. I was just showing the sea ice, sort of the sea ice in 1980. At the minimum or at the maximum melt. So when the ice is minimum, extent is minimum versus the present day. I can give you some links for those. They're not showing up here, but this is the important plot. So this is the Arctic sea ice area. This is in millions of square kilometers, and this is over time. So we're over here. So this here is if you take all the IPCC models, Intergovernmental Panel on Climate Change models, there's a whole bunch of them. There's about 20 different places in the world or something that have these very sophisticated climate models, and they all have predictions on sea ice. And those models all follow within this range of the gray or blue curve here. That's all of the models, their extent. And this is the mean of all those models, so the ensemble of the forecast. So this is what we have. And this is our observations. Clearly the models are completely breaking down. If you track, this is what happened in 2012. This was the latest year. So it was a huge drop from the previous year. It was a huge drop from the previous minimum. But not only is the area of the ice declining, so the end of the melt season is about mid-September when the sea ice area is minimum, and but the ice is also getting very, very thin. So this is just some different regions of the Arctic and the sea ice thickness. So this is measured. This is submarine data from 58 to 76 using submarines during the Cold War would surface through the ice. They measured the thickness. They also had some radar units which were pointing up, and they could measure the thickness. So this is showing the thickness in these different regions. So there is variation across the Arctic. And then more recent submarine data, 93 to 97, a huge decline in thickness. And then this is satellite data, ISAT data. So it's showing an even more larger decline. 2007 was the previous minimum year. But since then, we've lost a huge amount of ice. You can't see it on this particular plot. So, okay, so what happened this summer in terms of sea ice melt? Well, the ice was the ice rapidly declined. But what happened is there's other phenomena happening in the Arctic as the ice declines that makes it a non-linear system. And one of those things that is most crucial is that as the sea ice is declining, there's a lot more open water, and and the water is warming rapidly because it's darker, so it's absorbing more energy quickly, and that it's creating there's more evaporation from this water, so there's becoming more moisture in the atmosphere. The Arctic is normally like Antarctica, considered like a desert. It gets very little rainfall because it's cold. Warm air can hold a lot more moisture than cold air, a lot more. It's an exponential effect. So what's happening is we're getting these large storms in the summer in the Arctic, and that's very unusual. So this is a cyclone. This is Greenland here, and this is Siberia up here. So this cyclone was a massive size. It covered most of the Arctic. It went through, this is an image from August 6th. This cyclone churned up the sea ice. It went from August 2nd to August 10th this year. And it destroyed 0.8 million square kilometers of sea ice. That's about 20% of the ice that was left at the previous minimum in 2007. So how did it destroy it? Well, it churns it up, it breaks it up into smaller pieces. That increases the surface area, so it melts. There's more open water around, which is warmer, so that mixes with the ice and melts it. When ice is melting, the water around the ice is just slightly above zero. Seawater freezes typically about minus 1.8 degrees Celsius. So when that melts, the fresh water around it is very cold. So if that's churned up by a cyclone with water from below, like the water below, deeper down on 50, 100 meters down below the ice is a bit warmer. And the cyclone actually, there were buoys that were 500 meters below the ice that measured an increase in temperature, and they measured a vertical movement of water, because the cyclone is a low pressure area, and it lifts up. You get a storm surge, basically. You get the water lifted up. So when the water was lifted up, water had to enter the Arctic, both from Bering Strait, so that's warmer Pacific water, and also from the Atlantic side, and also through the little channels through the Canadian archipelago, and that water was all warmer. So that, as the cyclone lifted up the water in the basin, water had to surge in, and then as the cyclone left, after over a week, then the water would go back out. So the cyclone was also, the winds of the cyclone were also pointed directly out of into the Atlantic. So a lot of the ice was actually just ported out into the Atlantic. So that's why the ice was massacred. And these storms are also lasting a lot longer. Normally, when there's a cyclone in the Arctic basin, it lasts for a couple of days. This one lasted 8 or 9 days, and one recent paper said that these things could last even 30 days. The other thing is that it was so large, it was drawing in air from Siberia and also over the Canadian archipelago. And there were a lot of forest fires in Siberia at the time, so this air coming in had a lot of soot and so on in it. But it was also 20 degrees Celsius air, so it was very warm. So that was fueling the storm. So this, if there had been another two storms like this, that probably would have finished the sea ice off this last summer. Okay, but this was a very sort of unique event. These things will become a lot more common as there's more and more water, open water in the Arctic. These type of storms will be more frequent, and they will. That's one of the main reasons for the nonlinearity. So the ice isn't just melting; like it's being ripped apart. So the volume is what is key. Like most of the plots on sea ice you'll see are on the area of the ice, but this is the ice volume over time. This is observation. Okay, so it actually takes the sea ice area, it takes the thickness, and it's a model. It tries to get the volume, and this is the data here. And this was 2011 data point. I haven't marked on 2012, but it's down here. So this thing is tracking down. So if you do a fit to this curve, just a fit to the observation, it goes through 0 at 2015. So this would be about this would be the most likely year at which the sea ice vanishes according to this trend. This is a 5% error, 5% probability location at 2013. This is a 95%. So greater than 5% chance of vanishing by 2013, greater than 50% by 2015, greater than 95% by 2019. And that would be vanishing at the end of the melt season. So the first year it vanishes, it might be gone for a couple of weeks, or it might be gone for all of September or something. But this model doesn't actually even incorporate the cyclone. Like it doesn't take into account that the cyclone activity can speed up this. It doesn't take into account the fact that there's been upwelling of warm water from 500 meters deep in the region. It doesn't take into account the number of cyclones. None of that stuff. It's just the observation. But those things kind of explain why the drop is so steep. So let's say the ice, is gone by. I look at the ice. The ice now. I was just looking. I look every few days at what the ice is doing. There's some great websites where you can get everything. One website, one-stop shopping, everything you want to know about sea ice. And the ice is, it's not very thick. It's not growing back. The meteorology in the Arctic is messed up. There's no other way to describe it. Normally, we have a lot of cold air up there, but right now there's a massive warm area, a ridge, very powerful ridge cutting directly across the Arctic Ocean, because we have heat still rising up from the open ocean. Parts of the Arctic Ocean are still there, and we also have methane levels are going up, and methane is a very powerful greenhouse gas. Methane's coming up from the seafloor. It's also coming up from permafrost. We also have the snow cover is much, much reduced. So it's not just the sea ice going that's severely decreasing the reflectivity or albedo of the Arctic. It's also there's much less snow cover over the land. So the land is darker than the snow. So that's contributing to the massive amplification of temperature. So what this is this lower curve is the plot I showed you of the September minimum, and these are just all of the different months. So this is the ice volume for all of the different months. So it's not just the September minimum when the ice is less ice. Every month is having less ice. So what you can do is, if you say take the 50% chance of ice vanishing in 2015, the ice will be free. The Arctic will be free for about a month in September, say in 2015. The next curve, if you go up another year, right, then there's 3 months that fit into that category. So you could say that the ice would probably be free. You'd have a ice-free Arctic in, say, July, August, September, within about a year or two of the first bit vanishing. And within about 9 years or so, within about 3 years, it's free. The ice free duration is 5 months. Within about 9 years, there's no ice year round in the Arctic. And obviously, we've got a massive change in climate, because the sea ice, as I said, is the linchpin to the jet stream, which controls the extreme weather. So we're heading there. We're heading there very quickly. So what is it? So one of the things this is manifested is there's huge. If the jet streams are in different locations, and the storms basically track the jet streams. So these these storms are occurring in different places, and because of the higher water vapor content in the atmosphere, these storms are much more intense. So you're getting intense rainfall events some places and droughts in other places. So in this image here, so this is extremely dry areas, extremely wet areas. So 50% of the U.S. had either a top 10 driest or a top 10 wettest year in 2011. This was unprecedented. Extremely wet part of the country were 32% versus a norm of 10% of the area, and extremely dry where it was about 22% relative to a norm of 10%. So basically the climate and is the movement of the jet streams is changing the statistics of the weather system. So when you hear of somebody saying a 100-year flood or a 1,000-year event, okay, those you need to really think of the climate as the old climate and the new climate. So those statistics were valid in the old climate, but they're no longer valid in the new climate. We haven't had time to get a handle on what they are in the new climate, and how can because we're going through an abrupt transition, we're going to see things changing differently from year to year. So I'll speed up a little bit, but so this, we know that in March of this year we had this massive heat wave. So this shows the anomaly, 15 degrees Celsius, massive anomaly. This was an example of water in Lake Michigan, how it would normally heat up during the year and what it did during the event. But this was an off the scale, unprecedented, one of North America's most extraordinary weather events in recorded history. Well, that will be broken probably in a year or 2 years or 3 years, right? We think of this year and last year as extreme weather, but in a couple of years we won't even remember the events of the year because we're going to see a lot more. So anyway, the growing season it started 5 weeks early. In Ontario, all the buds were blooming, and then there was a killing frost in April, which destroyed 88% of the apple crop. So, but the main thing, is that the U.S. drought, because you have these very extreme waves, you have the jet stream is very extreme like this. These waves up here, it's very warm because it's getting air from below. Down here, it's very cold because it's getting air from above, and these areas kind of get fixed to the continent. And you can relate. The U.S. drought would not be as severe, would not be, you can relate it directly. You can start relating these events to the climate change. But this is vast areas of the country. The water levels on lakes and rivers is very low. So this is important because in the rivers, if the water temperature is too warm, you have to shut down nuclear plants because you don't have the water's not cold enough to cool the reactor. Also, right now, there's a huge problem on the Mississippi because the water is so low, the barges are getting stuck near St. Louis, and they're having to dredge and let more water in from reservoirs. But, as this drought is ongoing, the Mississippi could shut down as a transportation route, and that's I think 25% of U.S. Exports goes through the Mississippi. So we're talking about huge economic implications of this. Another active hurricane season. Sandy would not have... Sandy turned left, very, very unusual. It couldn't go north because of a blocking high. It was pulled to the left because of a low pressure region, directly as a result of these extreme waviness in the jet streams. And it was a massive storm. It brought up, of course, the huge storm surge. We're also seeing, right now in California, we're seeing a phenomenon called the atmospheric river. I don't know if you know, but in about 150 years ago, 170 years ago, occasionally there's these events where these atmospheric rivers, they stretch across the ocean and it's very high water vapor, and they come into the west coast and they rise because of the mountain and they deposit huge amounts of rain. So, and I think it was around 170 years ago this happened, and it rained for 43 straight days in California. And it deposited so much water that there was basically a lake formed in the lowland areas. It was 400 miles long by 20 miles wide. It covered Sacramento with 10 feet of muddy, dirty water, and it took 6 or 7 months to evaporate. And this happens every couple hundred years or every 150 years. We can measure it in the sediments and so on. This event that's happening right now is this type of atmospheric river, but it's only lasting for for 3 or 4 days, but it's bringing about 20 inches of rain to parts of California, 10 inches to others. So, but the with climate change, with more water vapor in the air, with the jet streams changing, these events will become more frequent. So, that would have a huge effect, of course, because it would hit some of the really good agricultural regions of the country. We're getting things like derechos, which are straight line winds of hurricane speed. These huge dust storms in the deserts and so. So anyway, the statistics is basically changing. I'll go up a bit quicker because I want some questions. But in a nutshell, the greenhouse gases are going up, so we're getting more warming. Sea ice is melting. So that's leading to an amplification effect in the Arctic and increasing methane levels because it's coming out of the sediments and the permafrost. So that moves the jet stream, right? It moves and it bends. So it causes extreme weather, floods and droughts. And, we get lots of fires because it's much drier. Fires produce greenhouse gases. We're in Colorado. We're having another major fire right now, 70-mile-an-hour winds. Massive fire, it's traveling over huge areas. Crops fail because, we don't know when to plant. We don't know, it's either too wet or too dry. I mean, Britain, a lot of their crops have been failing because it's just too wet. Of course, in the U.S., we're having massive failures. When we had that heat wave in Moscow in 2010 and flooding in Pakistan, that was because of the jets, and we lost 40% of the grain crop in Moscow. They didn't export that year. So, there's no other way to describe the net result to us. So, you'll have a copy of this presentation. I have a lot of different articles and stuff to document what I'm doing. I mean, this is my research, looking at the big picture, looking at the connections between all the systems. So you can have a look at that. This is a kind of a busy. This is the statistics of the system. So what it's showing is that in these time periods, 55, 65, 75, the red areas are, so this is hot June, July, August. This is summer hot regions and cold areas over the land only. And this is this scale is standard deviations from the norm. And then the numbers are the amount of they're the size, like 10% of the area is above 3 sigma of standard deviation in terms of the warmness of the area. Back up here, it's 0% was 3 sigma, 2% was of the land area was 1 sigma, right? And then down here, we're talking 10%, 17%. So what's happening is these numbers here that are closer to the norm are all shifting to higher standard deviation. So the statistics is changing. We're having a lot more parts of the surface of the Earth being, 2 sigma, 3 sigma warmer events in the norm, and much fewer being colder. So the whole, if you think of the bell curve and then the average temperature, well, we're shifting that whole curve up to the right, so we're getting more and more extreme events. We're seeing events that we haven't seen before. So we had a massive ozone hole over the Arctic in 2011, a massive ozone hole. This makes sense because with higher greenhouse gases, we warm the lower atmosphere, cool the upper atmosphere because we get less light going up there to heat it. So the upper atmosphere dropped below this threshold temperature at which these ozone and chlorine would go onto the surface of these clouds and the ozone was destroyed. So we lost 40% of the ozone layer. We only normally hear of the ozone layer destruction in Antarctica, but it happened in the Arctic for the first time. An article just came out yesterday that by Mike D'Souza and one of the scientists on the main paper looking at ozone. We have a lot of monitoring stations in northern Canada. The Harper government didn't allow them to talk about their ozone paper. It was squashed, and that's happening a lot with government scientists. This is we all know about sea level rising, and it's rising more. Another thing is the pH of the ocean. The pH of the ocean's become about 30 to 40% more acidic in the last 30 years, because the CO2 in the atmosphere is absorbed by water droplets in rainfall and then goes into the ocean and makes the ocean more acidic. This is a problem for the food chain, obviously. These are just some plots showing the rise of melting of both Antarctica, the Arctic, and overall. This is talking a bit about the methane sources. We have this huge area of the eastern Siberian Arctic shelf where the methane is coming up big time from that region. I do have an image here. Okay, so this is the overall global measurement concentrations of methane. So we see a rise starting at about 2007, and this is coming from the Arctic. So this is methane bubbling up from the seafloor because the water is warming. It's melting the sediments in the seafloor. So just a couple of years ago, these plumes were tens of meters of diameter, and just last winter when they went up, these plumes are now up to 1 kilometer in diameter, and there's hundreds of them. And so 1 kilometer in diameter plumes with bubbles coming up, and it's methane. And methane is a very powerful greenhouse gas. We can see measurements in Alaska of the methane. It cycles seasonally, but then there's measurements up here spiking, measurements up here in Svalbard. So across the Arctic, the methane is increasing. But this is most striking here. This is 2006, 7, 8, 9, 10, and 11. And you can see the red is the methane concentration. So you can see that, there's been methane coming up for this decade, last decade, but, it's coming up in a lot more intensity. There's a lot more, and it's also adding to the warming. So this is going to affect food because, this is the drought severity index around the globe, and if you can compare, where the drought is projected to be, it's in food-producing areas, right? So food is how we're going to be affected most. So, this is interesting. This is a commodity index, right? So there's spikes during World War I, II, the oil shocks, and it's also been rising here. A couple of years ago we had record food prices, and the UN is predicting, they're giving warnings about global food shortages next year because of the. We have a cascading series of events. Ice-free Arctic, rapid warming, methane surges, mega drought, superstorms. Heat waves in the U.S. breadbasket affecting transportation routes, accelerating sea level rise, the Amazon rainforest. I have a presentation here which is about 80 or 90 slides of more details of all of this. You can have a look at it. It's all online. And I put Churchill's quote that, we're basically, this is a period of consequences. I am with the group, the Arctic Methane Group, and our view is that, we can easily regionally cool the Arctic, keep the sea ice there, keep the methane in place. We have technology to do that, but there's no political will. But that would allow us to keep. If we did that, that would allow the jet streams to be somewhat stable, and that would give us time to slash emissions, because that's the only way in the long term to stop us changing into a different climate. And then this is just my lab at the University of Ottawa. So I went over a little bit, but I'm happy to answer questions.
Okay, I just was wondering, near the beginning of the presentation you had, there was a really remarkable difference between the Arctic and the Antarctic, where the Arctic looked like it was all warming ridiculously fast. And the Antarctic was kind of some of the coldest regions, and yet some hot as well. And I was wondering why such a huge difference between the two poles. If you could just briefly.
Okay, so the sun is strongest at the equator. Like it's like a flashlight on a wall, and the beam is circular at the equator. The sun's directly overhead. So the intensity, the amount of light per unit area is large. As you go to the poles, the flashlight beam becomes very oval, right? You're at a sharper angle. So the area is much larger. So the intensity, the power per unit area is smaller at the poles. So the poles are heat. That's why the poles are colder in general. The Arctic, because the white snow and ice are decreasing, being replaced by dark ocean or the dark permafrost, then that's absorbing more of the light. So there's a lot of more heating up there. In Antarctica, it's warming in Antarctica for most of the regions, but if you go from minus 45 degrees Celsius to minus 40, you still have a lot of ice, right? It's not like the ice is melting. The Antarctica is losing ice because the ocean is warming underneath, and a lot of the Antarctica is sitting on bedrock that is below sea level. So the water is coming in that's warmer and melting it from below. And we can measure that from satellites, but also the geography is quite different in the Arctic. There's no, you can go completely around the planet at a given latitude in the Antarctic, and the ocean currents can go completely around, and the air can go completely around because there's no land masses in the way. So this creates a Antarctic circumpolar system, with very fast winds, very strong ocean currents. It kind of isolates Antarctica from the rest of the planet. So that's sort of it's quite different because the Antarctica is ice on the continent, and the Arctic is sea ice over the ocean for the most part.
Is this how the world ends?
Yeah.
I wouldn't say this is how the world changes for sure. It really kind of irks me to see these projections of global population hitting like 9 billion by 2070. Totally ignoring climate change. I think climate change has a very strong potential to severely reduce global population, and I think the rate of change is very unprecedented. So I think that if people become smarter, and if I was running the show, I'd be cooling the Arctic in the next few years and keeping the sea ice in place and slashing emissions, and we could go on and have our nice comfortable lives. But I don't see that happening politically. So we're going to lose the sea ice, and we're going to have massive extremes taking off, and the world is starting to wake up, and the politicians are starting to wake up. But oil companies are starting to say they want a tax on carbon now, right? So it's the politicians that aren't. So Obama should be up there giving a State of the Union address on climate change and how we'll deal with this. It's just like humans can be very stubborn and very slow to change, but once we get the will to do it, we can do things very quickly. Like change all the car manufacturing plants to producing tanks. It happened in less than a year during the war. We had our back against the wall. We responded. Well, we're reaching the stage, certainly, where our back is against the wall, so we'll have to start responding. So I stay positive.
It was you talked about that storm, the cyclone that churned up a lot of the water, and then the ice just started.
Yeah.
Okay. How about traffic? Have you guys seen a fairly huge increase in traffic, either commercial or tourists or whatever, and has it had an effect? Have you guys observed any effect? Or
I guess a couple of weeks ago, I was at the Norwegian embassy. They have a Nordic group, and the ambassador of Norway was talking, and in terms of as the ice is going, we have the Northwest Passage, which opens up north of Canada, but that's because a lot of the currents are pushing ice towards that. If it opens up, it can close off, a week later, and then open up, and it's less sure for shipping traffic. But there's also a passage on the Russian side, the northeastern passage, and that opened up, and it stayed open for over a month and a half. And the ambassador thought that there was. She sort of recalled that there was about over 300 ships that made that transit this summer.
versus
Normally you can't get any.
nothing?
Normally you can't get any, but it has opened up, in the last few years. So yes.
I was wondering about basically the thermal mass that's sitting on top of the Arctic that cools that and causes the jet stream. You mentioned as the delta T drops, it gets wavier. Presumably, also the amount of cold there is going to dissipate. Will we eventually see a period of stability with a much more constrained jet stream just kind of cycling up around the north?
Right. So
a zone of stability.
No. So like, where does this lead us? Is like in 10 years, 20 years. So So what I see happening is I look at the paleo records to see how quickly temperature and changed. And in the paleo records, we have many examples of cases where the average global mean temperature changed 6 to 8 degrees in 2 decades or less. I think we're going through an abrupt transition, and without sea ice, I don't see us having a real like a snow and ice in winter. We know that 50 million years ago, in a very warm period, we lost all the snow and ice and sea ice, and we had actually tropical forests starting to grow up in the far north. We had turtles, we had things that would die with the temperature drop below zero, and they thrived in the Arctic in previous periods in Earth's history. So I think you might be able to grow pineapple and pineapple trees in Ottawa like in a decade or two. I think it all depends on the methane. If the methane stays intact, then we'll transition. Maybe the models of 2-degree warming or 4-degree warming by 2100 will hold, but I just can't see that. Like I can see, I would expect like a 6-degree change in within a couple of decade or two, the way things are heading, because these effects all cascade. We're gonna. There's just too many factors that are coming into play. That's why I think it's vital that we try to keep the sea ice up there, because that's a tipping point of the system. Non-linearity just takes over, and then we can't do too much. We just kind of try to adapt and try to move away from the coasts and whatever. So.
Okay, well, join me in saying thank you to Paul Beckwith.